So, BIBO stability. Can we talk about BIBO stability for a nonlinear system? Yes, no, I do not know. Yes, yes, yes. Okay, we can talk about BIBO stability for nonlinear systems. In this course, we focus on LTI systems. For LTI systems, there exists a very simple way for checking BIBO stability. And it's a checking that will be done on h of t, that is my impulse response. Okay? So whenever we talk about LTI systems, we have this one, and we will check BIBO stability through checking this one. Can we apply this technique to nonlinear systems? No, because nonlinear systems do not have an impulse response that is a meaningful thingy to do operations together. So, two mistakes that often people do. BIBO stability only for LTI systems? No. BIBO stability for any system. Whenever we talk about LTIs, we have an additional tool. Can we talk about BIBO stability of a nonlinear system by analyzing the property of the impulse response of this nonlinear system? No, because a nonlinear system doesn't have an impulse response that is a useful tool to do things, because superposition principle doesn't hold. How much are we together, people? 1, 2, 3. Perfect. So, we are going to be able to graphically do explanations, people. Very interesting. First definition, absolute integrability. Function, signal, absolute integrable if modulus of the signal, we take the integral, it converges. Okay? Let's make an example. T, f of t, and then we take this signal here. This one, absolutely integrable? Yes, why? Because this area is finite. This one, absolutely integrable? No, because that area is infinite. This one, absolutely integrable, etc., etc., etc. No, because we do not take the integral of the function, but the integral of the absolute value of the function, and the absolute value of the function is this one. Together, if I take f of t equals sine of t, this one, absolutely integrable? Yes, no, I do not know. No, okay? Because we get this one, we need to analyze, that is going to be area that is infinite, okay? Together, so the examples that we did, this one, an exponential, 0 and then the exponential. This one, e minus t, e minus alpha t, e alpha t with my alpha negative, for t bigger than 0. The area here, is it finite? Yes. Integral of an exponential, you get the exponential. How much time do we have? Not too much. One over t. For t, so let's make something more meaningful. 1 over t plus 1 for t bigger than 0. It looks like this, true? In time. True? Absolutely integrable? Yes, no, I do not know. That means this area, is this area finite? Infinite. People, this one, I see, but it's like, I don't know what to say. Are we together that this stuff here, the area behaves like a logarithm? Whenever you take the integral of 1 over t, the integral of 1 over t is a logarithm of t, true? If you do the derivative of logarithm of t, you get 1 over t. Are we together? Logarithm of t, what does it do? True? Goes to infinity, true? So this area behaves as a logarithm as time goes on. This area goes to infinity. This one is not absolutely integrable. Are we together? If I was taking something like this, or any power here strictly bigger than 1, then the area is finite. Do you remember the stuff here, people?
So to know if it's a finite, it's a integral.
This is the definition. Okay. We have an f, we have a function. We have a function. You take the absolute value, you take the integral. Okay, take the integral. Is this one true? Is this true? If yes, absolutely integrable. If not, not absolutely integrable. So if we take the avocado of all the functions, there's going to be some that are going to be absolutely integrable and some that are going to be not absolutely integrable. Are we together? Okay? Perfect. Depends on f. Don't mess up with this kind of e exponentials go down, go to 0, stop. Okay. As soon as this one is negative. Okay. It's finite, very big number, but finite. Even more important. T to the power of m e alpha t with alpha strictly negative. Also this stuff here for t bigger than 0 and 0 otherwise. Okay. I'm always taking those causality. We are going to discuss a little bit better about causality later on. But for now, I'm taking this kind of version for which I give an impulse to the system and it's going to start responding. It doesn't respond before. This stuff here is absolutely integrable. Because this one goes to 0 faster, much faster than this one goes to infinity. Okay? Together? For any m and any alpha smaller than 0. The number might be very, very, very big. It's going to be a gain. We will see it later. But are we together that this stuff here, as soon as this one is negative, this stuff here is absolutely integrable? Are we together, people? Okay. Theorem. We are not going to prove it. We are going to see the implications. An LTI system, non-autonomous LTI system. If it is autonomous, we cannot talk about BIBO stability. An LTI system is BIBO stable if and only if the impulse response is absolutely integrable. We take H, we look at it, we take the absolute value, we do the integral. Is that integral finite? Yes, BIBO stability. No, not BIBO stability. Let's do an example. I do not have a lot of time, but we are going to see some examples. And if this is going to start, what am I plotting here? Here I'm plotting the convolution of a sinusoid and another sinusoid, the two sinusoids that are not in sync. You see? The stuff on the bottom is the output. The stuff in the middle is the product. You see? This is my input, this is my impulse response. Whenever I've got, which impulse response might it be? Which physical system might have this impulse response? without friction. True? A mass spring without friction is something that responds to an impulse. I hammer it, it starts oscillating. This is the impulse response. I'm flipping and translating it, but you can see it. True? What happens whenever, stop. Whenever I have an input that is with the same frequency of the impulse response. This is the case where my input and my impulse response are having what? The same frequency. From a physical perspective, this is, I have a spring mass system, and it's the equivalent from an energetic point of view that every time that it's oscillating and passing through zero, I push it, and I push it, and I push it, and I push it. What do I get? It explodes, true? Because in a certain sense, I'm injecting always power in the same direction, energy in the same direction. While if I go to this situation here, I hope it's this one. No, I got to go back. I think this video here. Sorry, I'm making a little bit of a mess. Whenever I go to this situation here, the input is injecting energy, sometimes in the right direction, sometimes in the wrong direction. What do I get? I get this kind of oscillations, but I do not get something that explodes. True? You see it? Are you see it? Are you seeing it, people? From a physical perspective, what is happening? Stop this stuff here. I'm drawing on this axis here, that is omega, and this is 0. If I put x here, it means that I'm considering a certain sine of a certain omega t. Okay? If I have my h that looks like a sine here, and my u that looks like a sine here, whenever I do the convolution, I do not get something exploding. True? True? From an avocado perspective, it means that I have this u is this specific point. The h is actually the transformation, true? Because h as a convolution operator, convolution plus h operator, it's something that maps something from here to here. Are we together? The function h. Together? If I take this u, I go in this y. That was the one before, the one that was doing this kind of stuff. But as soon as I get this u here, I get where? I get unbounded. Okay? You see that in a certain sense, with this specific H, with this specific spring mass system without friction, for which the impulse response is not absolutely integrable, I am able to find an input. There exists a bounded input that leads me to an unbounded output, unbounded force response. Okay? So it's not able to. Let me see it.
Repeat this concept of the frequency it explodes? What that implies with regard to this theorem?
Certain frequencies, whenever I take sine as a h, a certain sine omega t with a specific sign, an omega for the u that is different from omega bar are going to bring me inside in the second avocado. But if I take an omega for the u that is equal to the omega of the impulse response, this one is going to make me explode. Okay? And for the BIBO stability, we say that, but it's enough that I find one thingy in the kernel here that leads me to the mid out for having instability. True? Doesn't mean that for every u I have unbounded y. It's enough that for one bounded u I get an unbounded y to say it's not BIBO stable. How much do you feel we are together, people? 1, 2, 3. Are there questions? I see some few tools, but I do not know what is not clear. Yes. Yeah, so we cannot use it as a probe. Delta as an input doesn't live here. Delta lives here. And we don't. If I said it, it was something stupid that I said. Look at me. If I take as a probe signal this one, and I get this result, can I say something about the Baldo stability properties? No, because I don't care. I care about what happens in this transformation, true? If I take an example that is this one and goes inside, can I say something about BIBO stability properties? No, doesn't care. I need to start here and see where starting from here I go, okay? Delta, does it live inside here? No, delta is unbounded, true? So delta lives here. I can't use it as a probe, okay? Together, we go on Tuesday. Actually, Tuesday we meet. Wednesday I'm not here. Wednesday I'm in Olesund. So you do with Christian the assignments. But Tuesday I'm here. Okay. So we do Tuesday and Wednesday. We are not gonna do this lesson. Yeah.